Assalamualaikum. We are going to present our MSD2 with our title Chill Water Plant with 5,000 RTD capacity. I'm Arif Kamarudin Razak with Majid ID 22741. So I'm going to explain about introduction. We shall start with overview first. This project is primarily to design a chill water plant with 5,000 RTD. The conceptual is main focus on the functional and physical decomposition. So the factors that need to be considered is the required production capacity with the highest efficiency. The important thing is we choose the system carefully so as it may consume the most energy. So the purpose of the chiller is to cool the water in most cases, as the chillers cool a mixture of water and other chemicals, most commonly added with low temperature application to prevent freezing. Other additives can be used to alter fluid properties, making it more suitable for its intended use. So moving on to the problem statement, as we know, conventional air conditioning will produce high power and consume high electricity bills. So this chiller we need to design with its own unique characteristics so it can fulfill the capacity needed. So the issues, does it can operate 5,000 RT according to the requirements needed, according to the specification that we have endorsed. So it is compulsory to have the detailed analysis regarding to the design of the system to ensure that it can work perfectly. Moving on to our objective, to determine the feasible configuration, we select the suitable chiller, select a high efficiency cooling tower, select a suitable thermal storage. The next methodology, so we did the preliminary research. We identified the best type of chiller, we identified the basic configuration, we proposed the design of chiller, the sizing of components and the equipment have been identified, we evaluate the capacity and COP, we did the analysis and discussion, and lastly we made the conclusion. So the scope of project, we identify the suitable type of chiller, we design the chill water, then we identify the appropriate operating condition, we study the effect of the thermal energy storage on the operating expenditure, we design the test thermal energy storage, we determine the appropriate capacity of the main equipment, we propose a suitable equipment, and lastly we study the economic feasibility. We move to the next presenter.
Okay, alright. Okay, my name is Amin, and I'm going to present about the literature review part of this project. The literature review will contain the hybrid system, electrical chiller, and thermal energy storage tank. Okay, the first is hybrid system. Hybrid system is known as a centralized air conditioning system. The hybrid system normally consists of electric chiller compared to the absorption chiller. The purpose of having hybrid system is to increase the energy efficiency of the building and at the same time increase the green index of the building. Okay, the hybrid system will provide both heating and cooling service to the building. It consists of two loops, primary and secondary. The primary loop will handle chiller system, and the secondary loop will handle AHU system. Okay, the means to transfer the chilling or heating effect to the building is by having a coil or heat exchanger. Okay, next, I will explain about the electric chiller, or known as a vapor compression chiller. Basically, the electric chiller will powered by electric to run the compressor. Okay, this type of chiller using refrigerant. This type of chiller normally require less initial investment, but the requirement for the chiller is to have the highest COP, which is around 4 to 5. Okay, this type of chiller normally have 4 stages. The first is compression, second condensation, third is expansion, and fourth is evaporation. Next. Okay, next I'm going to explain about the thermal energy storage tank. Basically, there is two types of thermal energy storage tank. First is chilled water system, and the second is ice storage system. The purpose of having test system is to take advantage of lower electricity tariff during off-peak period. The construction material that are used to build the test tank are concrete and steel. The main component of the test tank is foundation, shell, bottom, roof, and nozzle. To design this thermal energy storage tank, we need to comply with the FTI 350, which suggests the following formula, which is a one-foot method. Okay, the summary of the literature review is, we need to a chiller plant is a part of hybrid system. The electric chiller must have the COP of 4 to 5 to comply with the industrial standard, the test tank is required to reduce the operating cost and the chill of the chill water plant. The test design should follow the API C150 standard. Okay, moving on to another presentation.
Right, my name is Muhammad Azhar bin Muhammad Khalid. My ID 23045. I will present my part, which is the proposed design. We move on to the next slide. Proposed location. As per design, our design was 500 RT or 5000 RTH that will be produced. There are many applications for this type of capacity, such as the small airport, high-rise, high building, offices, for the shopping mall, and etc. But we are highlighted by choosing our location to the industrial park. Our chiller operation philosophy is running and will be recharged during the night time, between 10 hours to 12 hours. And the product of the chiller will be stored in the thermal energy storage as stated by Shami just now. This is because during the night time, we can reduce the operation cost like the electricity consumption to run the chiller. And also because during the night time, the temperature is already stopped and it make the operation become high efficiency. We move on to the next slide. This is the plant sizing where we can see time 100 meter times to 40 meter. And then the plant design, this is the basic concept, the process flow of our chiller system. As you can see, there is a cooling tower, pumps, cooling water pumps, and chill water pump, and also the air handling unit. We move on to the conceptual design. These have been stated and described by Shami just now, where we have the compression, condensation, expansion, and also heat removal, and finally our product will be stored in the thermal energy storage. There are 4 primary components in the system. First, chillers, and 2 pumps, 2 cooling towers, and also thermal energy storage. This is our schematic diagram. As you can see, this is the basic overview about our schematic diagram and about our process of chiller plant. Then the plan layout and detail drawing. This is our actual design, where you can see the equipments in this drawing, such as the 2 pumps, 2 chillers, and 2 cooling tower. Design have been calculated, and we will choose the design based on the market as per design. The only thing that we design in detail are the thermal energy storage. And we move on to the next slide. This is our thermal energy storage design in detail, where we can see the radius of the tank is about 20 meters, have been calculated. Then the calculation, I will describe about the calculation for the thermal energy storage. From the our obtained data, as you can see, our design is 500 RT, and we have our constant water density, specific capacity, temperature in and temperature out that we have decided, and also the time of operation per day, which is we will run during the night time. And then we will plug in this value into the equation to find the volume, flow rate. From that, it will time the 10 hours, and we will get the total water required to run our chiller plant. And then to calculate our thermal energy storage design dimension, we choosing our shape in the cylindrical shape, and the formula is by volume of the cylinder. We will plug in our input here and we will get the radius. And the calculated height is around 10 meters. As per report, our calculation have already included of the safety factor around 25%. We will pass the floor to the next presenter, Muhammad Farid Aiman.
I'm Farid Aiman and I'll be presenting on the chiller design. Firstly, we set our refrigerator mass flow rate to be 13.3 kg per second. We set our pressure at the evaporator of the chiller to be 320 kilopascal, and we set the pressure at the condenser to be 1200 kilopascal. From there, we are able to obtain sorry for the delay. We are able to obtain all the enthalpy values. From the enthalpy values, we can calculate the QH, WIN, and also the COP. The QH we get 2123, the WIN is 364, and the COP is 4.82, which meets the industrial standard. Next is the cooling tower. The QH we obtained before from the previous slide, and we set the temperature to be change in temperature 6 degrees Celsius. Then we plug in all the values into the heat energy equation, and we will be obtaining the mass flow rate of the cool water to be 84.46. Volume flow rate in meter cube per second is 0.084, and the volume flow rate is 5067 liter per minute. As for the pump, there are two pumps. We use the incompressible fluid flow equation. From there, we derive the equation and to find the head. From the head, we obtain all the specification for pump 1. And we obtain the pump head to be 13.94 meters. With added safety factor and also the brake horsepower and efficiency, we obtain the brake horsepower to be 16.36 horsepower. As for the pump 2, we use the same equation, which is incompressible fluid flow. The pump head obtained is 8.88 meters. With added efficiency and safety factor, the brake horsepower obtained is 11.26 horsepower. Now I pass the floor to the next presenter for project costing.
Hello, my name is Ahmad Adil Aizad bin Baharuddin with student ID 22729. I will present the part for the project costing. Project costing is the total fund needed to complete the project or work that consists of both direct costs and indirect costs. The project costs are any expenditure made or estimated to be made, or monetary obligation incurred or estimated to be incurred to complete the project, which are listed in the project baseline. Such as for this construction project, which require the cost estimation starts from land acquisition costs, construction costs, material costs, administration costs, labor costs, and other direct and indirect costs. Thus, the project success is divided by how well the project cost has been handled in the project. Hence, it's very important to come up with the correct cost estimation needed for the project. For this project, the criteria of the project costing divide into two types, which is COPEX and OPEX. First, COPEX. First, CAPEX. CAPEX, capital expenditure, commonly known as CAPEX, are funds used by a company to acquire, upgrade, and maintain physical assets such as property, building, and industrial plant, technology, or equipment. CAPEX is often used to undertake new project or investment by the firm. Making capital expenditure on fixed asset can include everything from repairing a roof to building, to purchasing a piece of equipment, to building a brand new factory. This type of financial outlay is also made by companies to maintain or increase the scope of the operation. The table is shown the capex for this project. The detail for this capex, such as for the equipment details, is obtained by procuring the market, which try to find the equipment which specifies our needed based on calculation done before. Here is the summary of the capex. Next, on the upcoming slide, I will show this the equipment that we are going to procure from the market for our project. The first equipment is the capex. Capex, as you see here, is a model YMC2 S8000 AD, which have the cooling capacity of 18,000 kilowatt, but the required is only 175 at 0.43 kilowatt, which satisfies the requirement for this project. Next equipment is the pump chill water. This pump chill water pump power is 15 kilowatt, but the required based on the calculation is only 13 kilowatt. Next is the pump for the cooled water. This pump has the power of 18.5 kilowatt, but the requirement is only required 16 kilowatt. Last but not least, the next one is the cooling tower. This cooling tower for our project required of 15.2 meter cube per hour, but this cooling tower can supply 165 meter cube per hour, which satisfies the requirement of our project. Last but not least, the thermal energy storage. This thermal energy storage, 90,000 gallons, satisfies our requirement for our project. Next is for the OPEX. OPEX, this is the operating expenditure, often abbreviated as OPEX, is an expenditure a business incurs through its normal business operation. OPEX expenses can vary widely depending on the industry and the nature of the business itself, but most of the operating expenses can be classified in these categories, such as for rent, payroll, marketing, research, maintenance, subscriptions, utilities, legal fees, and among others. But for this project, we focus on three types, which is the utilities, management, and maintenance for our OPEX. OPEX is one of the typical responsibility that management must contend with, its determining how to reduce the operating expenses without significantly affecting a firm's ability to compete with its competitor. For the upcoming slide, I will focus on the utilities and management for OPEX for this project. First, the utilities of OPEX for this project. For the utilities OPEX, it consists about the electric base tariff, energy consumption daily, and electric cost daily. And based on this detail, we're able to get to sum up the utility cost annually for this project, which is 368,854.4 cents. Next is the management cost for this project. Here is the list of OPEX management costs for our project, which justified by year. As you can see at the end side is the total OPEX management for each year, from as shown here, from year 0 to year 15. Next is for the total project cost. Total project cost is a vital step for any project, which should include the cost, fixed and variable, fixed cost or variable cost of the project. The calculation should include the total estimated cost (TEC) and other project costs or PC. For this project, we focus on the capex and opex of project, and from that detail, we're able to construct our break-even analysis to identify at which point we will be able to achieve break-even for our project. So to show that, we conduct our break-even analysis, and with our data, we're able to construct an annual cash flow diagram, which can be shown here at the 14th year of our project. This project will start generate profit. Lastly, for this project costing, here is the project cost summary of this project, which is summarization of capex and opex. The blue section is the capex with its details, as just stated before, and the opex, the green color. And lastly, at the overall total cost is the total project cost for this project, which is required around 3,535,810.98 cents. That's all. I will pass the floor to the next presenter.
I'm Faraiman. I'll talk about the project management. Firstly, the project schedule. We list down 5 main components, which are analysis, design, procurement, construction, and commissioning. Here are the start date, end date, and also the duration. Then from that we obtain the work breakdown structure. We divided it into 5, which are planning, background research, engineering and detail design, project costing, and procurement and commissioning. Below are the details of each components. Once we obtain the work breakdown structure, we make a project chart which shows the details of each day and date, and when is the completion of the project. We will start the project at 17 September 2019 and ends at 17 of April 2020. After the project chart, we make the critical path management. Firstly, we do analysis. Next, we identify the data, physical and functional decomposition. Next, we select the final concept. Once we select the final concept, we generate the governing equation. Then we determine the volume flow rate of chilled water using heat energy equation. Then the next step is divided into 3 main components. Firstly is to determine the work required for the chillers component by referring to vapor compression cycle. The second is identify the total volume of chilled water required for the thermal energy storage. Then we determine the size of the chilled water for designing the thermal energy storage sizing, volume of cylinder equation, using the volume of cylinder equation. Once we obtain that, we acquire the pump capacity using incompressible fluid flow equation. The third one is determine the amount of heat energy for the cool water using the heat energy equation. Once we obtain that, we determine the flow rate of cooling water using the heat energy equation. Once we obtain that, we acquire the pump capacity using incompressible fluid flow equation. Once the 3 main components have been completed, we will do the final drawing. The final drawing will be reviewed by Dr. Amin. Once it is approved, we do the procurement function, construction, and also the commissioning. In conclusion, for our chiller, the refrigerant mass flow rate is 13.3 kg per second. We set the evaporator pressure to be 320 kilopascal, condenser pressure to be 1200 kilopascal, and our COP have met the industrial standard, which is 4.82. The chiller's work is 364 kilowatt. The cooling tower, we set the change in temperature to be 6 degrees Celsius for heat reduction. The thermal energy storage is, we design the shape to be a cylinder. We set the radius to be 10 meters and the height is 9.62 meters. With that, the chilled water flow rate is 4,196 liters per minute. From there, we get the pump capacity of 60.36 horsepower. As for the cooling water, the flow rate is 5,067 liters per minute and the pump capacity is 11.24 horsepower. Overall, we achieve required performance and have a COP that follows the industrial standards, and our objective is achieved. That's all from us. Thank you.